Good morning, everyone, and welcome to Engineering 201 Statics. I believe this is week 3 lecture, and today we're going to be going and finishing up chapter 2, sections 2.8, 2.9. Kind of a short day. Just some miscellaneous things. Again, we're in like week 3. You should be in sort of class 3, class 4-ish. In unit 1. Just note the deadline there, and then the first exam will be right after that. So unless there's any questions through the chat, I will just jump right into things here now, starting in chapter 2.8. Looking at forces, vectors along a line or through a point. The first part of this class, up until now and through a little bit of next week, we are looking at force vectors in 2 and 3 dimensions, and we're presented with the vectors in a number of different ways, and we have to know how to deal with them. And in no particular order, we've been presented with a Cartesian vector form. So if I have this drawing, I'm just going to use this existing drawing over here. If I have a force acting here and it goes up and it says F, and it puts in here, I don't know, 100, negative 60, 200 newtons. If we had a force like that, we should call that one number 1 because it lines up with this one. That means we're given the force already in Cartesian vector form. And that's really where we have to get all forces into that format to be able to do things with them later in the class, like sum the forces, find the resultant force, find the moment of that force about a point or axis, and deal with them. So that's the ultimate, is where we're trying to get all of their forces into that format. And again, it's just cut off there, that little arrow on top. So that's the first one, Cartesian vector. Sometimes we're given that, and that's awesome because we don't have to do anything with it. And after this unit and after this first test, the book is going to assume you know how to get those. So it's not going to ask you to find the force in Cartesian vector form. It's basically going to start right from that. So definitely need to know how to do this. Second one is using direction cosines. And if you remember, direction cosines are the alpha, beta, and the gamma. It's pretty lame, beta there. Sorry. Got to do that again. Alpha, beta, gamma. In direction cosines, we use cosine, and they show the directions. And the important thing about them, and we don't have one here, so I'm going to draw one. The important thing about that kind of force, if we make that F2, because it's 2 here, that we're going to know the angles measured from the 3 axes. So alpha will be from the X, the Y will come over here and give us the beta, and then from the Z axis, we come down here to get gamma. So if a force is presented with those angles, be careful, because the ones that are shown here, there's 45, 30, and 30, are not technically direction cosines. I mean, this one we could argue is, because it is measured from the x-axis. So technically that could be an alpha, but typically we're shown at least 2 of those, if not all 3. And if you remember, if we don't have all 3, we can use this identity. Come on. To find a third one. So if we're given 2, we can find the other or last one. So that's given in direction cosine format. And to build that vector, let's put over here. So F1 is already to go. F2, we take the magnitude and we multiply it by the cosine of all those to build that vector. And there's the arrow on top. So that's a fairly easy way, and used in conjunction with that identity, sometimes we can get there. All right, the third type, again, these are in no order. The third type would be dealing with angles off planes. Now, direction cosines are angle off axes. That's important. These are off planes. So 3 would be this one, and 3 could also be that one. I'll call that 3B. There's 3A. Excuse me. We're given the angle 30 degrees here. And when we're given the angle off planes, we can use sine and cosine to find the components. So the first one here, F3A, if we're going to build that, that would be the magnitude. The x-axis would be cosine of 30 in the I direction, plus 0 in the y direction because it's off that plane. That's what that shaded triangle is showing us. It sits in the xz plane. And then we'd have a minus 300 sine of 30 degrees in the k direction. And then have units of Newton, so we'd put those in there. Now, why is that minus? Because right here it's going below or negative. That's positive z up, that's in the negative z direction, and that's why it's a negative there. And sine is the side opposite, giving us that side of that triangle there. Sine gives us the side opposite. And then we'd reduce that to be, whatever it is in newtons. Whatever 300 cosine is, 300 sine is going to be half of that, so that's 150. Also with the angles off the plane, the second way is a little more complicated, and it's this one over here. Let me just get a different color. Orange it is. Here we have these triangles, and these are right triangles. But this one here is in the XY plane, and this one here is in the, well, what is that? That's sort of the Z and between the X and Y plane, but it's a vertical plane. And the way we have to deal with those is using this sort of up and over idea. What we're going to do is take the vector, which is right here, at 500, and we have to bring it up or cosine it up to put it into the XY plane. So to do that one, let's do it up here. We're going to take the 500. We have to bring it up to the XY plane, so that's going to be cosine of that angle, which is 45. Now it's here. Now it's in the XY plane. Now we have to either pull it or push it back to the X and Y. For the X direction, we have to bring it all the way over here. And if that's 30, that means this angle is going to be 60. So we have to cosine 60. That's going to be the over part. Here's the up part. And that gives us the I component. Doing that again, let's do the Y component. Plus 500. 45 cosine, remember, brings the up. That brings it up to the XY plane. Now we just have to push it over there, which is going to be a cosine of 30, and that gives us J. It's in the positive, so I can leave it. Then the last one is get the K direction. Since it's below the XY axis, we're down here in negative K area because it's going that way. We just need this side right here. And that side is a side opposite the 45, so that's going to be a minus 500 sine of 45 degrees K, and then we put units, all that, and then we get that answer. Nope, not yet. All right, let me take a second, because that's always a confusing one for students. Let me just take a second and see if anybody asks a question in the chat. Okay, I'll take that as everybody is up. Two-step process to normalize. In this last one where you have the two, it's below a plane, yes. You have to bring it up and over or bring it up and push it back. And also remember to stay in degrees, have it calculated in degrees, because if you're in radian, you'll be all over the place. No problem. All right. Last one I think we've gone through, I don't think I missed any others, is this last one dealing with that small triangle. The small triangle. And let's see if that's more of a 2D one. Let me just draw it down here. The small triangle one is when we're given, obviously, the direction of this vector. Let's say it's 100 newtons by a little triangle. And let's say that's a 3, 4, 5. It's always going to be a right triangle. Other ones I think are what is it? 5, 12, 13? No. Well, we'll get to it. Anyway, so we're given this. There's the X and the Y. Now, again, we could go through and figure out the angle here because it's going to be the angle inside that little triangle. But the easier way to find these components and to find, instead of finding that angle, is knowing that cosine is the close side. So cosine of this angle theta is equal to the close side, that's 4 over 5. Sine of that angle will be the side opposite, which is 3 over 5. So instead of going through and calculating what that angle theta is, and then going back and cosining that angle, or sining that angle, we can just substitute in this ratio. So for the X component, I can write 100. Instead of cosine of the angle, I would just write 100, 4 over 5. That gives me 80 in the I direction. In the Y, I would take 100. Instead of sine, I would put in 3/5. And that's going to give me 60 in the J. And I think that's way easier than trying to find that angle through tangent or whatever, and then going through and cosining and sining again. So whenever you see that little triangle, again, there's other ones just not coming to right now. That's the fourth one. Excuse me. So I think up until now, that's how we've seen forces presented or represented. I put presented and represented here on drawings. Any questions with those right up till now? Those four-ish different ways we're going to see it. Okay, let's get to the one that's actually today for lecture, where a force is represented or presented as going along a line, like for a cable or a rope or some support guide wire, or between points. Okay, and I'm going to jump in here and put another page. And let's see if I can, nice. And that's going to be continued because we really didn't do anything on the last. There. All right, so let me draw an example of what's going on here. Do I want to do that yet? Yeah, let's use this. I'm going to use this, and then I will Yeah, let's use this one. And then we'll do that as an example here. Oh, doesn't like me doing that. Give me a second. Hello. There we go. Need a Simon Says first. All right, along the line or through points. Okay. So along the line and through points. All right, we have two forces shown in this drawing here. We have the F1 is 150 and the 200 is F2. Now they're basically showing us the same force here. This is through points. Through points because it's starting at point A and it goes to point B, or starts at point A and goes to point C. So this is really showing us, you know, there's from A to B and there's force going from A to C, and that's the 150, and here's the 200 newtons through those two. So that's really through points. And what is showing up here is that the force starting point is A. So at point A, it could have, I don't know, it could have some eyelet up there that's in the wall, or some sort of other anchor that it's tied to, or it's nailed there, or just, it doesn't really tell us because we don't care so much. In statics, what we're really trying to do is find all the forces that this object, whatever this thing is part of, in reality, we're trying to find the forces that act on it in the moment, sort of the maximum of both of those. And then they go back and say, all right, the maximum force on this thing, the result is going to be 175 newtons acting at some direction. And then the designers are going to take that using design code and this stuff and strength of materials and material science. And what they'll do is they'll design that anchor to withstand at least that much. Okay, they don't just go out and buy and say, hey, just go get an outlet from Ace and we'll use that. No, they're going to say from us what the maximum we expect that to undergo, what the maximum load is. And then they're going to go and say, all right, we need to design one. Then it gets into some following courses to do that. So all that to say is we don't need to know right here how that's connected. It doesn't matter for us. We just know it's connected at A and it goes in that direction from A to B, or it pulls from A to C. And what we're just given is magnitude, but we have the 2 points so we can build that vector. Okay, and that's what we're going to go through today. Along the line is the same thing. Along the line is, yeah, it's essentially the same thing. I'm just trying to think of what other options to draw that. You know, if we had this anchor over here at D and we're just pulling that force and it goes through some coordinate point E. So that's along the line. Same idea. These two being the same thing, but we usually have 2 points. Here we have D and E, so we'll have coordinates of D, and we have E. We can find it. Same thing as this, just that the force here extends beyond. Okay, and that's an important concept we'll bring up later, in that I can make this even longer, and it doesn't change the force that's in there. It's like if I have a rope attached to a wall and I'm standing here and I'm pulling on it, it doesn't matter if the rope is that long or if I stand out here and pull with a rope that long, it's going to be the same force. Okay, the force is still transmitted through. The only thing I'm really getting here is just distance, because maybe I don't want to stand next to this if it's going to fall over on me, so make it taller. All right, so that's what we're dealing with, through points or along a line. Same idea. How do we deal with that? Well, let's look at AC here because it's already up. So I'm going to look at this AC, and it's going force AC is going to go pull from A to C. And I'll get a different color here. That's kind of lame. To C. All right, first thing we want to do. Always the first thing. Now, you may be able to do this once you learn how to do this. You'll probably be able to do this sort of on the fly, in your head, write it out. But I see this as a place that, because it's so easy to start, we sometimes just mess the math up because the math is so easy. All right. So what I want you to do is first write out the coordinates for both of these points. All right. So if we're looking at A, let's see, where's the origin? Back in here, right? Origin back in there. So to get to that point, we have to go 0 in the x. So that minus 1.5 in the y, and then up 4. And I don't have my correct glasses on here right today, so if you see me make a mistake, let me know. And what that means is I have to go 0 in the x, I walk negative 1.5 in the y, and I walk plus 4 in the z, and I should get to that point. And I can put meters up there to remind me. All right, the coordinate C. That looks like it's at 3, positive 3, a minus 2, and then a 0 because it's sitting right on the plane. And 0 because it's sitting right on the plane. Okay, any questions on that? All right, so we definitely want to get that coordinates there from A to C. All right, so what do we do next? Well, we're trying to go from A to C. So we want to build the position vector. Remember, that's the R. This position begins with P. Position vector from A to C. So we want to take the C coordinate and subtract the A coordinate from it. So for the X or the I direction, we're going to have 3 here minus 0 I, right? The C minus the A, plus minus 2 minus a minus 1.5, right? Minus a minus, don't forget that minus, that's in the J direction, plus 0 minus 4 in the K direction, that all have meters. So what I should end up with a position vector from A to C equaling, I'll just do the shorthand here, 3 minus 0.5 and minus 4 meters. And that's my IJK. If we're doing the other one from A to B, we take the B coordinate minus the A coordinate. Same idea. All right, the next thing we're going to do is get the magnitude. Why do we need the magnitude? Well, what we're shooting towards, what we're looking to do here is if I take the position vector over its magnitude, it gives us the unit vector, which is a small u. And from the unit vector, I can find the force vector. I can build that final force vector. Remember, that's where we want to get to. Force vector in Cartesian vector 4 by taking the magnitude of that, which in our case is the 200, and multiply it by the unit vector. So the force vector is Fu. I know it's kind of silly, but maybe it'll help you remember. So to find Fu, we take F and we use the position vector. So this is what we're working towards building here to solve this. Okay. And I'm going to see if it lets me, I'm running out of space here. Nice. All right. So there we go. That was sort of the little interlude. That's what we're trying to get to, building the force along that line. All right, the force along that line. Find the unit vector, and again, the unit vector just points in the same direction. It's unitless. That points in that direction for us. All right, so we found I'm just going to get a little different color here. We found the position vector, so we have it there. And let's find, so we found this top part right there. Let's find the magnitude. Again, the magnitude of any vector, if it's in 2D, and I have it here, it's, it's 3, 4. So it's 3i plus 4j. Nope, have them backwards. 4i plus 3j. If I want to know the magnitude, which is really the hypotenuse, I'm going to square both and take the square root. That's Pythagorean theorem. We do the same thing in 3 dimensions, sort of like Pythagorean's theorem for 3D. So what we're going to do is take 3 squared, again using this, 3 squared plus minus 0.5 squared plus minus 4 squared. We take the square root of that. That gives us the magnitude of that position vector, AC. And if you go through that mathematically, see if I have it written down here somewhere. It's a little over 5. It's like 5.02, something like that. That's the magnitude. What does that mean? That is literally the length of that line there, or the distance between A and C. You may have done that in calculus. Sort of distance former in 3D. All right, to finally build our force vector now, that's what we're looking for. Force vector of, we'll call it AC because it's from A to C, is going to be the magnitude, which is 200, times position vector, which is the 3i minus 0.5j minus 4k, divided by the magnitude, which we found over here, which is 5.02. Now, as you can see, we deal with the coefficients, the 200, 3.5 minus 4, and the 5.02 in the bottom. But the I, J, and K's don't divide out if you want to think of it that way. So we're going to have an answer that's still an I, J, K, which is what we want. That's Cartesian vector form. And if we go through that, we get 119 minus about 20 and about minus 160 newtons. And that would be our answer in Cartesian vector form. To write another way, 119i minus 20j minus 160k. All right. All right, let's do a quick little, how do we check that? I mean, how do we look at that? Obviously, the calculator gives us an answer. How do we have any kind of thoughts that maybe that's even close to the correct answer? Is there a way we can do that? Yes, we can. We're starting at A, we're pulling to point C. The idea is that force needs to pull in the directions we're given. So 119 in the positive X. Is it going in the positive X that way? Yes. What about in the Y direction? It has to be pulling in the minus Y. Well, it's starting up here, and it's pulling back a little bit. Not a lot. Well, there's a little bit. And in the Z, it has to be, because it's negative there, it has to be pulling down, which that certainly is. So that gives me a little confidence that that answer is at least in the ballpark. Maybe not numerically correct, but it's in the ballpark, meaning directionally for the sense of it, it's pulling plus X, minus Y, and minus Z. And certainly more minus Z than minus Y. But that gives me some confidence. All right, one other way to check this. That force, those components if I take them and square them, 119 squared plus minus 20 squared minus 160 squared, and take the square root, it should give us the magnitude of 200. And that's another check. Why is that true? Because the force vector is a vector, just like a position vector is a vector, or a unit vector is a vector. Right? If I square root this, all the squares of those individual components, I should get the original magnitude or length. Another way to check. All right, nice problem there. I like that problem. I like that problem so much that when I go study for the exam, I'm probably going to come back here and really spend some time to make sure I understand how to do that. That's just me. All right, I'll take a moment here. Any questions on that, dealing with forces along a line or that pull between 2 points? Okay, again, I have lots of practice problems, not lots, but I have a few practice problems within my lecture notes that are posted in old PDFs from a few years ago. I understand my handwriting is not the best, but it's certainly better than nothing. And the book has example problems, and obviously there's a ton out there on the web. You can literally search on Hibbeler's chapter 2.8 or Hibbeler force along a line, and it'll bring up lecture videos and example problems that you can work through. And here's the key. And I made this mistake in college. It's really easy to bring up this solution, right? My messy solution, and look at it and say, yeah, that looks right, which I appreciate. Yeah, it does look right. But you have not learned how to do this, because when it comes time for the exam, you'll be presented with a problem and you have to solve it. And what we're really trying to learn here is not so much the math, but more the approach. How do I approach this problem? So if you're given this problem here that had the two forces, how would you approach it? Well, you have to build them, build the Cartesian vector form of the forces, and then we deal with them afterwards, which we'll talk about more next chapter. But we have to know how to approach it. The math is a smaller part. Obviously, it's important. I don't want to freak any math people out, especially my office mates. But we have to have the approach. I have to know how to build a house. Not just I know how to use a hammer. No, I need to know how to build the house. What needs to happen first? What happens to happen next? Dig the foundation. After permits and all that, dig foundation, build that, build the first floor, build the second floor. So here we really need to know the approach. So when you do these problems, or you're reviewing problems that are already solved, like mine and my solutions, or yours and your notes, or this with the video, start out, look at the problem, and cover up the solution. Because if you look at the solution, all you're doing is confirming the solution for that exact problem. And if you get a different problem, you're kind of in a little bit of trouble. So force yourself. This is the best way for this class. I tell everybody every year, force yourself to solve these problems. And you don't have to solve them all the way through mathematically at the end. Just how would you approach it? Just page through the book. Go through a handful of problems in the book. Just looking at the pictures and saying, all right, how would I approach this? What do I have to do first? Because typically once you figure that out, the rest is just following sort of our recipe that we're coming up with here. All right, so force yourself to do that. All right, any questions? A little off there, but trying to give you some help in how to be successful here. Lectures are recorded, and then it takes a few hours or overnight, and then they show up again in the same place where you join the lecture time, the link. But in the upper left, there's a little, they call it a hamburger. At least that's what I'm told, or a burger. There's a little icon that looks like this. Sort of, if this is your screen, here's our tabbing and stuff. Here's all the lectures and office hours. Right above it, right here, if you click on that, it brings up a menu, and one of them is recordings. You go in there and they show up. Okay, again, it won't show up. They have to process it. And I'll make a note of that in the class just so everybody else sees it. All right, so let's move into the second thing we have to cover. This is very brief. I'm not going to spend a lot of time on this. You should have seen this already in calculus. I'm not sure which one. Is the dot product. Okay. The dot product allows us to find the angle between two vectors. Okay, the angle between. Now, if we're in 2D, new color. If we're in 2D, we'd use trig, sine, cosine, things like that. There's vector A, here's vector B. We'd set up some axes here, and we would use some trig to find out what that angle is. We'd find this angle, and then we'd find that angle. We'd basically find a difference. When we get into 3D, however, that you can sort of do that, and I know there are people, there are students that every year will try to, they just resist using the tools in 3D to solve things. They'll try to solve it using trig even when we're in 3D, and it is possible, but man, it gets messy. So I want to try to discourage you from trying to hold on to sine and cosine when you get into 3 dimensions. They're just, especially with cross product stuff like that, they're just way easier. So if you can just embrace 3D and force yourself to really understand it, it'll make life simpler in the end. Anyway, so in 3D, we're going to use vector methods, and this is just one of them, which is the dot product. Okay, so that's what we're going to talk about here. 2D again, trig here. The dot product we can set up is that if we dot A with B, the vector A and B, so again, that's, AXI plus AYJ and AZK, we're dotting that with the same thing in the B. So, we have them in Cartesian vector form. That will equal A, the magnitude, times B, the magnitude. So I'll put mags here. Times cosine of the angle between. That is the dot product rule. These are Cartesian vector form. Those are magnitude, and that's the angle between. This is the dot product. It's also known as, AKA, the scalar product. And that tells us what our answer will be. When I have a scalar, the product, meaning multiplication of these gives us a scalar, that means that's just going to equal a number, an amount. We're not going to have I, J's, and K's or any of that. Okay. Now, what's nice about this is really, it's very simple. When we dot this, what it really means is we're using the cosine, and cosines for our 3 dimensions, if we have, X, Y, and Z, these are all mutually perpendicular. So unless I'm multiplying the X of the first vector with the X of the second vector, anytime I go X to Y or X to Z, that's at 90 degrees, and cosine of 90 equals 0. So they all drop out, and what we're left with when we dot vector A with vector B is AX times BX, AY times BY, AZ times BZ, and that comes out to be some number. That's easy. There's no I, J, and K left, nothing else. Okay? And that's the dot product of 2 vectors. Now, since that comes out to be a number, here's where we can do something else that's kind of cool. Well, I don't know if math is cool, but you get the idea. We can take that magnitude that we just found, right, which is this, and we divide it into I'm sorry, here's the magnitude we just got. I'll put it in a box. And that's the, that's the A dot B right there. We divide it by the product of the magnitudes. So that's the magnitude of A times B. I won't put a dot there. I'll put a little X. That will equal cosine of that angle between. So we can do inverse cosine and find the angle between by inverse cosine of that dot product over the magnitude. Okay, dot product over the magnitude. And then from there, if we need even more, because that's so awesome, once we know that angle between, we can find the projection of, let's say, A onto B, because now we know that angle in 3D. We know that angle between, so I can basically cosine it, and it'll tell me how much of A is along B. And that might be useful at some point, but that's a neat little math thing. Okay. All right, so that is the dot product. Again, I'm not going to go real deep into it because you've probably seen it before. And what we're just going to do now at this point is just do an example. And we'll be on for today. So let me just pull up an example. I'm going to see if I can find a drawing instead of having to subject you to my drawing. Let me see if I can find something here quick. Just give me a moment. Take a breath, get yourself a drink quick. All right, here's a simple one just to get ourselves started. And this is more just for practice of the dot product. Then we'll have time. We should have time to grab another one. All right, given this force up here, and there's a pole. We don't know how it's all fixed and all that kind of thing. This looks down here. This looks down here like it's, connected to the ground or something. That's probably a free end, and we have that force pulling on it. And let's just find a few different things from this. All right, ultimately, we just want to find the force projected onto the pole. And the pole is basically origin to, it doesn't have a point there. We're just going to give it a point. We'll call it B. Right. That's rare that you need to add to the drawing, but sometimes that simplifies things. So we'll call it the pole from O to B. All right, so let's go ahead and solve this. Two vectors? No, not really, but yes. One vector is the force. So that's a 2, what is that, 2, 4, 10. And we are in kilonewtons. I'll put that there. The second one is basically going to be the pole. Now the pole isn't a vector, but once that force pulls on it, the end of it's going to set up some load in that pole, so there will be a force along the pole. And we get into that in a later chapter, but we can look at this. So let's sort of try to build the vector of that pole, and that's more of a position vector. All right. So again, when we're trying to build that position vector, and that's from O to B, because we're going to sort of treat the vector as this way. O to B, we want to use those coordinates. So obviously the origin is 0, 0, 0. That's an easy one. And B is going to have coordinates of, what is that, 2, 2, 2 minus 1. And that's meters. So our position vector here will be, again, going from 0 origin to B, we take the B coordinate, subtract the origin from it. That becomes really easy. That vector becomes a 2, 2 minus 1. Nice when things are along the origin or from the origin. Now we're going to check that by walking it. We should be able to walk that vector. So I have to walk plus 2 from the origin, plus y in the plus 2 in the y, and then minus 1. That should get me right to there. It does. That makes me feel confident about that position vector. And that's a good little habit if you can get into it. It takes an extra 4 or 5 seconds, but it should make your solution, you feel more confident with the solution there. All right, so if we're looking at the dot product, again, it's AB equals AB cosine of the angle between. I'll get off that green, that's kind of hard to read. This really becomes the force. So we're really dying, that's really becoming an F, and that's, we'll call it P just for the pole, so FP, right? Even though it's position vector, it's kind of the vector of the pole. All right, magnitudes. Well, how do we find the magnitude of that force? Again, we know the components. So if we go through the components, we can, and square root that, we have 2 squared plus 4 squared plus 10 squared, square root, that becomes what, 100, 16 square root of 120. That's a very nice number. Just short of 11. Yeah. Let's call it 11 just for easier math here. Right, it's 10.95, but let's use 11 because that'll help me just sort of go through the math. All right, that's how I get that one for the F. How do I get for the P? Same thing, but I'm going to use this. It's the square root of 2 squared plus 2 squared plus minus 1 squared. That's for a 9.3. Nice, like that. And again, what do those numbers mean? That 3 is literally the length of that pole, or the distance between origin and B. All right, so on this side, we're going to have 11 times 3 cosine of that angle between the two. And the angle between is this right here. I'll put theta right there. What do we put on this side? Well, again, this side, this is the dot product, and the dot product means I'm going to multiply the i's, the j's, and the k's towards each other, and then add them all up to give me the answer. So I'm going to take the x component of the force, that's 2. So let's sort of, I'll put it all together here. 2 times the x component of that, that's 2, plus the y component, that's 4. And the y component of the pole is 2, plus the z component, 10, and down here we just have a minus 1. So if I go through that, what does that become? 4 plus 8 minus 10. We get a 2 on this side, 33 cosine of the angle between. We can go through it and find the angle between here. Is going to be the inverse cosine of 2 over 33. 2 divided by 33. Second cosine, make sure you're in degrees. Comes out to be about 87 degrees, just shy of that. And again, I'm just rounding up quick. And that's that value right there, 87 degrees. So if you're asked to find the angle between two vectors or between that force and the pole, or two forces or two lines, that's how you go through it. Now, we were originally asked to find the projection of the force. So really what I'm going to do is take that force and cosine it and cosine it there. Okay, it'll tell me how much of that is on there. So I'm basically taking the magnitude, which is 11. So we're trying to find how much of that force is on pole, on P. So I'm going to take the 11, cosine it with 87. And so cosine times 11. Say it again. 87. There we go. Comes out to be 0.58 newtons. So that tells me how much of that, if I bring that down here, let me bring out that green color again. If I project that down, it tells me basically how much of it is directed along. Now, what does that number really mean? Well, that number means how much of that force, which is pulling at the end of the pole, is actually pulling or compressing the pole along its own axis. And that's important later for point B, excuse me, where it's connected, how much is it pushing into that connector? If that's a sliding connector, like if you put PVC pipe together, or I don't know, you're putting any pipe inside or anything inside of something else, that it's pushing it that way so it would keep it seated or connected. If we found that that was a negative number, it would mean that it's trying to pull that pipe out of the ground, which we wouldn't want at this point. All right, questions on that problem? All right, I hope everyone can still hear me. I have my computer here. Just all right, it's showing that I'm still talking on this side. And I'm not sure what the arrow means there, if that's like an okay or. Okay, good. All right. I wasn't sure what this is. You know, and I'm old, so I get it. Is that fixing the spelling above there from can hear you, or?
No, I had already said can hear you, and they were just agreeing with that.
Ah, so that's an agreement. That's what that means. Oh, look above. All right, I get it. Hey, I learned a new thing. I'm an old dog. No worries. Appreciate that. All right, my machine locked up for a second. I was just afraid I had missed something. All right, questions on that problem we just did?
I'm good.
All right, let's see about, see if I can pull one more up. Just one more quick problem here. Hang on. I just feel better if I leave you with two problems instead of just the one. All right. All right, let's do this. Let's do this problem here. One last one, sort of on the long, not long side, but I will what we're going to do is sort of skip the math or sort of blow through the math so it's quicker. Okay, this one I'll need to draw. This is one from some old notes I had. So just hang on. What we do, we have a pole that's coming out of the origin here, and it's along the x-axis. And we're going to have two forces that are part of this. We're going to call this point A. That force is going to pull up to C, which is on the wall. And this one's going to pull up to B, which is also on the wall. And I'm going to give you coordinates here. That's 15, 0, 0. B is going to be 0, 3, 8. And C is 0, minus 8, 12. All right. So two forces there pulling at the edge of this through the origin. It's sort of like support wires for that beam or that pole that's there. And we're going to look at this one. So for this problem, and again, these problems are very similar to what you're going to see in an exam. You're going to be presented with an image, and it's going to tell you how what to solve for. Blackboard will give you places to enter the prefixes, so you won't put the I, J, and K in, but it'll ask you for what's this result in Cartesian vector form. You'll put in the prefix or the coefficient of the I, of the J, and the K with the appropriate sign. Blackboard will then, when you submit that, Blackboard checks your answer with a plus or minus. Basically, it's sort of a plus or minus 10%, so rounding won't be an issue. You won't be docked for misrounding or not rounding. And then you submit your exam work that shows to support what you did, so I know that you actually did the problem, and kind of how it works. All right, so we're going to solve this. Let's find the angle between AC and that would be AB. Okay, angle between. We'll call that theta. We're finding the angle between those two forces. There's force 1 and the force 2 over here. You can't really see because it's right over the pipe. All right, first thing you would do, if you are not given the coordinates, the first thing you would do, and just here's sort of the process, is pull the coordinates. They were already given to us, so we don't have to worry about that. But if they weren't, we'd want to pull the coordinates out and write them for A, B, and C. All right, since we want the angle between, we're going to use the dot product. And again, I'm just writing out the process. You can sort of do this in your head. And with the dot product, what we're going to need is force vector, I'll call it AC, and AB, right? I can put the F right there, but just to save some letters and keep it cleaner, we need AB and AC in Cartesian vector form. And we need AB, AC magnitudes, because both of those are necessary for us to do the dot product, right? AP, AC dot has to equal AB times AC, and then we get the cosine of the angle between. And since we're looking for that, we have to know everything else. All right, so we have to build those. Now, we don't need to build those as forces because we're not giving any information about that. We could just build those as position vectors and use the position vectors as our vectors to use the dot product. Okay, hear that again. For the dot product, it doesn't have to be two forces. as you saw in the last problem, we had a force and a pole. It could be two poles, it could be two lines, two forces, two whatevers. We just have to put it in Cartesian vector form. So let's go ahead and do that. Let's go ahead and do that. A, B. We're going to make position vectors. If we're going from A to B, we take the B coordinate minus the A coordinate. So I'm going to try to build this in one shot here. A to B, I'm going to take the B, so that's going to be a minus 15. That'll be a 3, and that'll be an 8. Position vector that goes from A to B is minus 15I plus 3J plus 8K. And again, we can check that by walking. Let's walk it. Let me pull up a silly color here and we'll walk it. We have to walk a minus 15 along the X, plus 3 in the Y, and plus 8. So minus 15, 3, and 8. That should get us to it. Sorry, the big marker there. So we feel good about that one. Let's go back and build the AC. Same way. A to C, we take the C coordinate minus that. So again, another minus 15 because it's going back to this plane back here, the YZ plane. 0 minus 15, minus 8 minus 0, 12 minus 0. And again, we can walk that minus 15, minus 8, plus 12 gets us there. We feel pretty good about that one. All right, magnitudes. How do I get the magnitude? Well, the magnitude of any vector, meaning the length of it is the length of any vector, or the distance between the 2 points. So we have to take the cosine, we take the square root of all the squares. Okay. So again, that's minus 15 squared plus 3 squared plus 8 squared. And if we go through that, what's that? 225 plus 9 plus 64. That's 17.3. So right here, right below here is 17.3. And then if we do this one, same thing, square root of 15 squared, that's 225, plus 64 is 8 squared, plus 144, square root, we get 20.8. All right, so that's just finding the square root of the squares, kind of like Pythagorean's theorem in 3D. And correction on that. Those numbers should be over here on the magnitude side. I just put them in the wrong spot. They should be here. Right, we already have that figured out here. So that's 17.3 there. That's 20.8 there. Let's see, can I erase that? Look at that technology. All right, so on this side, we still have to do the dot product, right? I'm going to get rid of that just so we have a little room there. All right, so there's our dot product equation basically set up, ready to go. We want to dot those on the left side of the equation. So if we write that out, basically we're doing minus 15 times minus 15. Again, we're going to do the x times the x, plus the y times the y is 3 times negative 8, plus then we have 8 times 12. 8 times 12. And if I go through that, that's what, 225 minus 24 plus 96, 297 on the left side. Again, scalar product, dot product is a scalar product, so I should get a scalar, meaning a number, not a vector with IJKs. That looks right. All right, on this side, 17.3, 20.8. Still cosine of theta. If I go through and solve for theta, which is the angle between, that's going to be inverse cosine, just rearranging 297 over 17.3, 20.8. And if I go through that mess, 3 divided by 20.8, inverse cosine that, I get 34.4 degrees. 34.4. Now that's the angle between the two cables. If I want to get the angle between one of the cables and the pole, I would have to swap out, like if I want to know between AB and the pole, I would have to swap out this one for the pole, which is going to be, there'd be zeros and zeros in here, and then we'd have a different magnitude, right, which would be 15 over here, and then we just get a different answer. All right, let me stop there. Any questions on that? All right, I know you're dying to know, but what comes next? Okay, obviously what comes next is, let me get the right color here. It's chapter 3. And chapter 3 is talking about equilibrium of a particle. Now, a particle is just an object, a body, a thing. We think a particle is small, it doesn't have mass, but it has a place we can locate it. Object, a body is usually comprised of many particles, but it's still treated as one thing that's not going to deform and all that. Okay. Now, this should all be reviewed, so next week should be a really easy one, because if you remember from physics, static equilibrium, SE, was when you sum up all the force, it equals 0, meaning there's no acceleration. And you sum up all the torques, they equal to 0, meaning there's no angular acceleration. Those are the two conditions for static equilibrium. We're just going to deal with the first one first, and we'll deal with the second one later. And here we actually do a thing called sum of moments, which is the same thing. Physics, they call it torque, which is a force that's tends to want to rotate something. A moment is if you're the thing being rotated, from the object's perspective, instead of you're the person torquing something, you're being torqued, if you want to think of it that way. So this is going to be really simple, because we're just going to look at this one in 2D and this one in 3D, which is we sum forces X and Y. Here we sum forces X, Y, Z. Really straightforward. Shouldn't be any surprises. Nice, easy way. 3D gets a little messy just visually, but we'll walk through that nice and simple, and that finishes up what we need to do next week. And that puts us on track for our first deadline, I think on the 22nd, the night of the 22nd, and then our first exam. So I will stop there. That's all I have for you today, and I will again hang on to see if there's any questions. If everybody disappears, then I'll know you're all good. because obviously of all the students in this class, you are all the smart ones since you came to lecture. So I appreciate that as always, and I hope these are helpful. So I'll hang out. Let me know if you have any questions. Otherwise, have a great week. Enjoy the day. If anybody needs to stick around afterward, ask questions, they can. Question about the homework for class 3. Do we have to number 1? I think that's, let me check that. I don't have it in front of me. If you would just check that I'm asking you, it may be the same problem. I just want to make sure I'm asking you to solve the same way. Because in class 3, if it's slightly, okay, thank you, Jen. If it is slightly different instructions, yes, I'd like you to solve it that different way, but you can use the previous one just to check your answer. Not that I don't make mistakes like that, but I think I'm remembering other students asking the same thing last semester, and it's asking you to do it just a slightly different way. All right, anything else? Liking my pad here. All right, great. So I'll hang out. Any more questions? I'll be here. If not, enjoy the day, enjoy the week. All homeworks, all assignments are due, quizzes and homeworks are due by the deadline of the unit. I used to have deadlines every week, and usually in the first couple of weeks, people were missing them and they confused them. So I sort of backed off, and it causes you to have to be a little more disciplined with staying on top of things. But the first deadline is, I think, the 22nd for the first unit, which includes classes 1 through 4 or 5. But please do not wait until the last day, because what happens, you start uploading them and the internet goes out, or your computer, your dog eats your computer, I don't know, and you just don't get them submitted on time. Blackboard closes the unit, so you can no longer submit them, and then you have to email asking, just you give me your excuse and saying I have them, can I email them to you? And I'd say we're going to follow the syllabus, which is no late assignments. So all that to say is, at least if you're going to wait till the last sort of minute, wait till the last day and do it one day before to make sure you get them all up there. That way, if you have issues, you have the whole next day to figure it out. There's no late assignments, no partial. Missing 1 or 2 is not going to kill your grade, but you certainly don't want to make a habit of it. And again, the quizzes are to hopefully give you an idea what you'll see in the exam. All right, as I said 10 times already that I'll stop talking. I'm now stopping talking.